In this video, we're going to run through the key theory behind undirected graphs, which is the introduction to networks and decision mathematics for Module 5 of Further Mathematics. So just using the graph here, graph 1, we're just going to run through some basic definitions. Remember, a graph is just a representation of the pathways or connections between points. And in terms of networks and graphs, we talk about these points as being vertices. You'll see in some textbooks that vertices are perhaps called nodes, or in some of the content that you see online, but vertices are what we use in our study design. So here in this particular graph we have 5 vertices labelled A through to E. The edges are the lines that connect the vertices, and they show the connections between the vertices there. Adjacent vertices are ones that have a direct connection. So A and B are adjacent, D and C are adjacent, but A and C are not, because you have to travel through B to get there. A loop is a special type of edge. So we see that we've got a loop at A, and a loop obviously begins and ends at the same vertex without passing through another one on its pathway. And a loop, you must take note that when you're talking about the degree of a vertex, which is the number of pathways leaving it, or the number of edges leaving the vertex, that loop actually counts as 2, because you're able to leave either by travelling out this side or alternatively out this side. So it actually has 2 different pathways, which counts as a degree of 2. In total, A has 3 ways to exit that point or that vertex, so that it has a degree of 3. With our adjacency or our adjacent vertices, we're actually able to represent those things in what we call an adjacency matrix, and it's basically just a table, or represented in matrix form, which vertices are adjacent to each other. So I'll just shift that over and we'll draw it here. So I have a graph with 5 vertices. So to represent the adjacency matrix, I actually need to construct a 5 by 5 adjacency matrix. So if I just draw a matrix here, I'll just try and squeeze it in there, and let's label that so I can keep track of my vertices and know what connections I'm representing. So just A through to E on the rows and columns, and then what I'm doing in each of these elements is just writing how many connections there are. So from A to A we have one loop. It's one edge connecting A to A, so we just represent that with a 1, as opposed to when we count it as a degree of 2. So make sure you take note of that. A to B, we have one edge, so we represent that with a 1. There is no direct connection A to C, no direct connection A to D, and no direct connection A to E. And then we move on to vertex B. So B, we have connection to A, connection to C, so we'll represent that A, no loop at B, a 1 to C, no direct to D, no direct to E. Vertex C, down here we've got no direct connection to A, 1 edge to B. We actually have 2 different pathways to get from C to D, so we represent that with a 2. The thing to note as well, that those edges between C and D are called multiple edges. Anytime there's more than one different pathway, or more than one edge connecting the 2 vertices, that's known as multiple edges. And finishing off, so, oops, sorry, I've actually put that in the wrong spot there, so that should be a 0 in that loop, okay, 2 C to D, and no connection from C to E. D, again, no direct connection to A, none to B, 2 edges to C, there's no loop, and no connection to E. And E, you'll note E here is on its own. It actually has no edges at all connecting it to any other vertex in the graph, and it has no loop. So it will just have zeros in its adjacency matrix row and column. And what we call E is an isolated vertex. So it's sitting there all by itself. Now, just note, it is possible for E to have a loop and not be connected to the rest of the graph and still be considered an isolated vertex. One nice little thing to note with your adjacency matrix is if we were to draw a line down the leading diagonal, we should note that we have a mirror image on either side of that diagonal. Okay, so if we were to look diagonally away from that, we notice that all the numbers should follow the same pattern. It's just something to sort of keep in mind as a little check for yourself. A couple more last definitions. We briefly spoke about the degree of a vertex. So the degree is the number of ways out of the vertex, I guess is the best way of thinking on it, or the easiest way of thinking of it. And so what that actually means is, for instance, at B, I could travel along this edge to C, or I could travel along this edge to A. So that has a degree at vertex B would be 2. So 2 ways of travelling. The other thing to note is with your adjacency matrix, if you add up the values in the row, then it will also give you the degree. The one thing to note though is, remember the trick with the loop. So a loop in a degree counts as 2. So you have to remember that, so that then you can add up that the degree of A would be 3. Okay. Finally, with this sort of graph, one last thing, if you add all of the degrees of the vertices and divide it by 2, you will get the number of edges in the graph. Another nice little trick, something that you can know. And we will talk more about degrees of vertices when we look at Euler paths and circuits a little bit later on. Okay, a few more definitions. Another special type of graph is what we call a bipartite graph. And a bipartite graph means it has 2 parts or 2 sets of information which have connections between the sets but not within. So here, the example I've given here is very, very basic one. 3 countries competing at the Olympics, so let's say that's Australia, Brazil and Canada, and 3 events: equestrian, fencing and gymnastics. And so what this graph is showing us, that Australia competed in the equestrian, in the fencing and the gymnastics, whereas Brazil didn't compete in the equestrian because there's no edge connecting the 2 pieces of information there, but did in the fencing and the gymnastics, and Canada again in all 3. So you can see here there's no connection between the vertices in that top set, and again no edges or connections between the vertices in the bottom set. We look at bipartite graphs later on in the topic in relation to allocation problems. So that's one of the 4 key applications that you look at in networks. Okay, moving on to some last definitions. So a couple of things to keep note of. A simple graph. A simple graph is just something that has no loops, no multiple edges. So it's a basic form of a graph. Okay, so an example of that would just be something like that. It can have a circuit, but what it can't have is a loop or a set of multiple edges. An isolated vertex, we spoke about that one before. So you can't get to it. Now I've said here it has a degree of 0, but obviously if I've got a vertex like this that's isolated from the rest of my graph, it's still technically an isolated vertex here, but this one would have a degree of 2 because there are 2 ways to leave that vertex. So perhaps that's something we should cross out. A degenerate graph where all the vertices are isolated. You tend not to hear this term, but it's just something worth noting. It is possible to have a graph where there are just vertices and no connections between them. Unlikely to see it, but it is possible. Okay, some things that we'll talk a little bit more as we go through the applications and further into this content. A path is just a sequence of edges, so it's the way through a graph. So we tend to look at what is the shortest path, or how can we get from one vertex to another. A path is just simply a way through. A circuit, however, is a path where we start and finish at the same place. So a circuit would be we're heading through the graph and heading back, ending where we began. A connected graph is just a graph where there is a connection between each set of vertices. It is possible to get from one point in the graph to another point in the graph. So in other words, we don't have any isolated vertices. An isomorphic graph. Now, you tend not to see this term in further maths, but it's something you probably covered in general maths in year 11. An isomorphic graph is just when we take one graph, so let's say we take this one here, this example, and we draw it in a slightly different way. So we still have to have the same information present. So there still has to be a connection from A to B, a connection from B to C, a connection from C to A, but the actual picture itself looks slightly different. Same connections, same number of vertices, same degrees of the vertices, same adjacency matrix, just looks different. This comes into our content a little bit later on when we're looking at planar graphs. And finally, a subgraph is when we take one graph and draw a simpler version of it. And this is often used to either just sort of highlight the path through a graph, or potentially as an application when we start looking at trees and minimum spanning trees and things like that. Okay, in the next video we're going to have a look at more of the applications of undirected graphs, but I hope this was just a little review for you all so you can get yourself set up for that.